Alright, now we're going to show that the direct product of two groups, G and H, is also a group. So the product of two elements is given as follows. Remember, an element in a Cartesian product is an ordered pair, where the first coordinate is from the first left set and the right coordinate is from the right set. So the product of two ordered pairs is going to be an ordered pair. The first coordinate in the ordered pair is the product of the first coordinates, G times G prime, and the second coordinate in the ordered pair is the product of the second coordinates. Okay, I should say left coordinates and right coordinates. So what do we need to check in order to claim that G times H is a group? We need to check associativity. We need to check that there's an identity. And we need to check that there are inverses. In this video, we prove that the direct product of two groups is in fact a group. So first, let's prove multiplication is associative. Let's take three elements in this ordered pair, Cartesian product, x, y, and z. We need to show x times y times z is equal to x times y times z. Remember, x, y, and z are ordered pairs. So this means that x is equal to g1, h1, y is equal to the ordered pair g2, h2, and z is equal to the ordered pair g3, h3, where the first coordinates, g1, g2, and g3, are all elements in the first set, g, and the second coordinates, h1, h2, and h3, are all in the second set, h. So what do we need to see? We need to see what x times y times z is. Well, this is x. This is y times z. To make the reading a little better, I'm using square brackets for where we normally put parentheses. So the first element times the product of the last two is given by this formula right now. Well, there's not much we can do, so we apply the definition of multiplication to this y times z. So the second ordered pairs, it's, what do we want to say? Component-wise multiplication, so it's the product of the first two coordinates, comma, the product of the second two coordinates. So g2 times g3, h2 times h3. That is the ordered pair. That is the product of these two ordered pairs. So now we have this product of two ordered pairs. We know how to compute that by definition. It's going to be an ordered pair. The first coordinate is the product of the first coordinates. So g1 times g2, g3. The second coordinate is going to be the product of the second coordinates, h1 times h2, h3. Well, multiplication in G is associative, so I can move these square brackets over and get G1 times G2 times G3. And H is a group, so multiplication in H is associative, so I can move the square brackets on the second coordinate as well. And now if I go in reverse, I can see that this ordered pair is what I get if I multiply G3H3 times this ordered pair on the right. Why? Because this product, the first coordinate is G1, G2 times G3, and the second coordinate is H1, H2 times H3. Finally, we can factor this first ordered pair as well. Factor the first coordinates from the second coordinates. The first coordinates are G1, H1. The second factors in the coordinates are G2, H2. So we get this factorization. We see that we had x times y times z up here. And down here we have x times y times z. So in fact, multiplication is associative. Now we need to find the identity element in the direct product. So it's going to be an ordered pair. It turns out the right ordered pair is going to be the ordered pair whose coordinates are the identity elements in the corresponding groups. So let E be the identity in G, E prime be the identity of H. We claim that this is the identity of G times H. So let G be in the group and be in the first group and H be an element in the second group. To check that this is actually the identity, we need to check that this product is equal to G comma H. Right? Multiplying any element by the identity gives you the element back. And any element in this set is an ordered pair like this. That's the reason why we're doing this. So let's do this product. By definition, it's an ordered pair whose first coordinate is the product of the first coordinates, and whose second coordinate is the product of the second coordinates. Because E is the identity in the first group, E times G is G. Because E prime is the identity in the second group, E prime times H is H. So we see E prime is the identity of G times H. Finally, we need to figure out what the inverses are. And it seems coordinate-wise identities worked very well, so maybe coordinate-wise inverses will work well. So let's try that. Let's suppose that the inverse of an ordered pair is the coordinate-wise inverses. So inverse of the first coordinate, inverse of the second coordinate. What do we have to check? We have to check that this product is the identity. Well, let's do it. Multiply G inverse H inverse times G times H. Product of the first coordinates is G inverse G. Product of the second coordinates is H inverse H. G inverse G is the identity. H inverse H is the identity in H. We just showed that this ordered pair is the identity in the direct product, which means this satisfies the axiom of being the inverse for the ordered pair GH. Since GH was an arbitrary ordered pair of the Cartesian product, we've now shown every element in the Cartesian product has an inverse. So this is in fact a group.